The thermometer reads -38 degrees Fahrenheit. The wind screams across the Greenland ice cap at 40 knots. And standing on this frozen wasteland, 76 miles from the nearest human settlement, Darryl Greenamyer stares at something that shouldn't exist. A B-29 superfortress, intact, sitting on the ice as if it landed yesterday. But this bomber didn't land yesterday. It's been here since February 21st, 1947, 47 years entombed in Arctic ice. And what Greenamyer sees defies every law of metal degradation, corrosion physics, and common sense about what happens to aluminum alloy when exposed to sub-zero temperatures for half a century. The aircraft is beautiful, not destroyed, not stripped, not corroded into unrecognizable scrap. Beautiful. The fuselage reflects the pale Arctic sun like polished chrome. The plexiglass nose cone, which should be shattered, yellowed, degraded, is clear enough to see through. All four Wright R-3350 duplex Cyclone radial engines remain mounted to the wings. The propeller blades are bent from the emergency landing, but the airframe itself sits level on the ice, supported by its tricycle landing gear as if waiting on a runway in Kansas. Greenamyer approaches the forward entry hatch. His gloved hand touches metal that's been frozen for longer than most people have been alive. The hatch opens with a metallic groan that echoes across the emptiness. Inside, the bomber is a time capsule. The crew stations are exactly as they were left. The pilot's seat still has the sheepskin cover. The flight engineer's panel displays hundreds of circular gauges, their needles frozen at the final readings from 1947. On the navigator's table, there are pencil marks on a chart showing the intended route from Ladd Air Force Base in Alaska to Fort Worth, Texas. In the radio operator's compartment, coffee cups sit on the console. In the rear gunner's position, a magazine from 1946 lies open to page 17. This isn't a crash site. This is a preserved aircraft that experienced a controlled emergency landing and was simply left behind. The question that drives Greenamyer isn't why it's here. The historical record explains that clearly enough. On that February day in 1947, the Kee Bird, the actual name painted on the nose, referencing the cartoon character, encountered a catastrophic navigation error during a routine repositioning flight. When Captain Vern Arnett realized they were hopelessly lost over the Greenland ice cap with fuel running low, he executed an emergency landing so skillful that all 11 crew members walked away without injury. The U.S. Army Air Forces evacuated the crew but classified the bomber's location and abandoned it. The decision was economic and logistical. Recovering a B-29 from the Arctic interior in 1947 would cost more than manufacturing a new one. The Cold War was beginning. Resources were directed elsewhere. So the Kee Bird sat and sat and sat. Through 47 winters and 47 summers, though summer in this region means temperatures barely rising above freezing. Through decades when snow accumulated around it, then sublimated in the constant wind, creating a microclimate that somehow prevented the aircraft from being completely buried. The question that drives Greenamyer is something else entirely. Can we fly it out? Not dismantle it, not cut it into pieces and airlift them. Fly it out, under its own power, with its original engines, the way it was meant to leave. The question sounds insane. This is a 74-foot-long, a 140 iron-pound strategic bomber that hasn't moved in 47 years. Its fuel has long since been drained. Its hydraulic fluid has congealed. Its tires are probably frozen solid. Its electrical systems haven't received power since the Truman administration. But Darryl Greenamyer isn't asking if it's easy. He's asking if it's possible. And standing in the Arctic cold, looking at the preserved masterpiece of 1940s engineering, he believes it is. Greenamyer is 60 years old, but his reputation in the aviation world is that of someone who's been 70 for the past 3 decades, because he's accomplished more in high-performance aircraft restoration and racing than most people achieve in multiple lifetimes. He holds absolute world speed records in piston engine aircraft. He's rebuilt warbirds that experts said were beyond salvation. His workshop in Campo, California, is filled with projects that would make Smithsonian curators weep with envy. But this is different. This is the B-29 Superfortress, the most advanced bomber of World War II, the aircraft that ended the war in the Pacific, the platform that required such sophisticated engineering that its development cost nearly as much as the Manhattan Project itself. Each B-29 contained 55 000 individual parts. Its pressurized cabin was revolutionary. Its remote-controlled gun turrets were computer-assisted decades before computers became household items. Its Wright R-3350 engines produced 200 horsepower each, and were so complex that mechanics joked they needed a PhD to understand them. And Greenamyer wants to make 4 of these engines, which haven't turned over since 1947, run again. In the Arctic, with improvised tools and supplies that must be flown in. With no hangar, no crane, no proper runway, and no margin for error because the nearest hospital is a helicopter flight of several hours away if the weather cooperates. The idea is audacious to the point of delusion, which is exactly why he's going to attempt it. He assembles a team, not a large team, 6 men total, including himself. Bob Deimert, his longtime business partner. Rick Krieg, an aircraft mechanic with experience in radial engines. Gary Larkins, a structural engineer. Dan Schley, a fabricator who can build aircraft parts from raw materials. And his son, Darryl Greenamyer Jr., who handles documentation and logistics. They spend months planning, months acquiring equipment, months studying the technical manuals for the Wright R-3350 engine, thousands of pages of specifications, tolerances, assembly sequences, and maintenance procedures written in the technical language of 1940s military aviation. In May 1994, they arrive in Greenland. The first challenge is simply getting to the aircraft. The Kee Bird sits 76 miles inland from the nearest coastal settlement, a location so remote that it exists beyond the practical range of most helicopters. They arrange transport with a ski-equipped Twin Otter aircraft, shuttling equipment and supplies in multiple trips over several days. When the full team finally stands together beside the bomber, the reality of the project settles over them like the Arctic cold. They have 60 days. That's the window when temperatures are marginally survivable for sustained outdoor work. After that, the Arctic winter returns and the ice cap becomes genuinely lethal. 60 days to assess 4 engines that haven't run in 47 years. 60 days to repair, restore, or replace every system necessary for flight. 60 days to build an improvised runway on the ice. 60 days to accomplish what Boeing factories took months to achieve under controlled conditions with unlimited resources. The work begins immediately. We're approaching 10,000 subscribers, and stories like this, real engineering challenges, real human determination, don't reach the people who need to hear them unless you help spread them. If this rescue mission already has you hooked, hit that like button, activate the thanks feature if you want to support documentary content that goes this deep into technical history, and drop a comment. What country are you watching this impossible Arctic mission from? Now, back to the ice. The B-29 Superfortress wasn't just another bomber. Understanding why this rescue mission matters, why Greenamyer and his team would risk everything in the Arctic, requires understanding what this aircraft represented in 1945. The Boeing Model 345, designated B-29 by the United States Army Air Forces, was the Manhattan Project of aviation. Its development cost $3 billion, approximately $50 billion in today's currency. That's more than any other single weapon system in World War II, except the atomic bomb itself. In fact, the B-29 program consumed more resources than the atomic bomb program. Why so expensive? Because Boeing was attempting something that had never been done. Building a high-altitude, long-range, pressurized strategic bomber that could carry 10 tons of ordnance across 300 miles and return home. The technological challenges were staggering. The fuselage was pressurized, the first production bomber with this feature. This required a completely sealed aluminum structure capable of maintaining 8,000 feet of cabin altitude while flying at 30,000 feet actual altitude. The engineering tolerances were measured in thousandths of an inch. Every rivet, every access panel, every door seal had to be perfect. The wings were the largest ever fitted to a production aircraft at that time, 141 feet from tip to tip. They incorporated Fowler flaps that increased wing area by 20% during takeoff and landing, providing the lift necessary to get 140 pounds of aircraft, fuel, and bombs into the air. The engines were Wright R-3350 duplex cyclone radials, 18 cylinders arranged in 2 rows, each cylinder displacing 350 cubic inches total, hence the designation. These engines produced 200 horsepower each at takeoff power, driving 3-bladed Hamilton standard propellers 16 feet in diameter. But the R-3350 engines were notoriously problematic. They ran hot, so hot that engine fires were common, especially during the early B-29 combat operations in 1944. The cylinders were magnesium alloy to save weight, but magnesium burns at 300 degrees Fahrenheit once ignited. Mechanics called them the engines that wanted to kill you. Boeing's solution was revolutionary. They installed the first production engine fire suppression system using CO2 bottles, and they developed advanced baffling to direct cooling air across the cylinder heads. But even with these modifications, the R-3350 required constant, meticulous maintenance. Now imagine those engines sitting in Arctic temperatures for 47 years. Greenamyer's team begins their assessment on day 1 by removing the cowlings from engine number 3, the inboard engine on the starboard wing. What they find is simultaneously encouraging and terrifying. The engine is clean, no corrosion. The dry Arctic air has preserved the metal surfaces almost perfectly. The cylinder heads show no pitting. The pushrods are intact. The rocker arms move when manually actuated. Stiff, but they move. But when Rick Krieg attempts to rotate the propeller to turn the engine through a compression cycle, it won't budge. The crankshaft is locked solid. This is expected. The engine oil, probably military specification 1120 grade, a petroleum-based lubricant, has congealed into something resembling cold tar. Every bearing surface, every piston ring, every valve guide is coated with this substance. The oil galleries inside the crankcase are plugged with it. Kriegs delivers his assessment. We need to heat these engines to at least 60 degrees Fahrenheit and flush them completely before we can even think about rotation. 60 degrees Fahrenheit, in the Arctic, where the ambient temperature is currently -20. They construct heating tents around each engine using aluminum frames and industrial canvas. Inside each tent, they install kerosene heaters, Herman Nelson forced air heaters, the same type used to preheat aircraft engines in Alaska during winter operations. These heaters blast 150 BTU per hour into the enclosed space. It takes 18 hours of continuous heating before engine number 3 warms sufficiently to begin work. They drain the old oil, thick, black, sluggish fluid that pours like cold honey. 28 gallons from the engine sump. They remove the oil filter, a massive canister the size of a paint bucket, and find it packed with sediment and degraded oil additives that have precipitated out of solution over decades. Then comes the flush. They pour fresh aviation-grade mineral oil into the engine, rotate it manually using a specialized propeller-turning tool, then drain it again. They repeat this process 6 times before the oil coming out looks even remotely clean. While Krieger works on engine number 3, Diemert begins assessment of the fuel system. The B-29 carried fuel in 14 self-sealing tanks, 7 in each wing and forward fuselage section. Total capacity, 548 gallons of 100-octane aviation gasoline. All of it was drained by the crew in 1947 before they abandoned the aircraft. Standard procedure. You never leave fuel in a derelict aircraft because fuel degrades, corrodes tanks, and presents a fire hazard. But draining the tanks doesn't mean the fuel system is clean. Thousands of feet of aluminum fuel lines, dozens of valves, multiple fuel pumps, and 4 carburetor assemblies still contain residual fuel that has been sitting stagnant for 47 years. Diemert disconnects a fuel line at the firewall. He attaches a hand pump and forces compressed air through the system. What comes out is brown sludge, gummed gasoline that is polymerized into a varnish-like substance. This material has coated every internal surface of the fuel system. The fuel system must be completely purged and cleaned, or the engines will never run properly. Fuel injectors will clog. Carburetor jets will plug. Fuel pumps will seize. They develop a cleaning protocol. Disconnect every fuel line section. Flush it with solvent. Blow it clear with compressed air. Inspect it visually, then reinstall it. For the fuel pumps, complex assemblies containing spring-loaded diaphragms and check valves. They disassemble them completely, clean each component individually, replace the rubber diaphragms with new ones brought from California, and rebuild them according to technical manual specifications. This work is painstaking. A single fuel pump contains 47 individual parts, including tiny springs, brass fittings, and precision-machined aluminum housings. Each part must be tracked, cleaned, and reassembled in exact sequence, and they must do this for 4 fuel pumps per engine, 16 fuel pumps total. While the engine and fuel system work progresses, Gary Larkins begins structural assessment of the airframe. His concern is simple but critical. Is the aircraft structurally sound enough to withstand flight loads? The B-29 was built using 24ST aluminum alloy, an aluminum-copper alloy with excellent strength-to-weight ratio. But aluminum alloys can suffer from stress corrosion cracking, fatigue, and cold-induced brittleness. Larkins begins at the wing root, the point where the wing attaches to the fuselage, which experiences the highest structural loads during flight. He removes inspection panels and examines the main wing spar, a massive I-beam structure that runs the entire wingspan and carries the primary flight loads. The spar is perfect. No cracks, no corrosion. The bolts that attach the wing to the fuselage show no signs of loosening or thread damage. He moves to the landing gear. The B-29 used a tricycle configuration, 2 main gear assemblies that retracted into the inboard engine nacelles and a nose gear that retracted forward into the nose compartment. Each main gear assembly consisted of 2 wheels with pneumatic tires connected to a complex oleo strut shock absorber system. The gear is down and locked, frozen in the extended position. The tires are flat but surprisingly intact. The rubber shows checking and surface cracks, but the structural carcass appears sound. However, the hydraulic system that retracts the gear is another matter entirely. Hydraulic fluid, military spec MIL H5606, a petroleum-based red fluid, has been sitting in the lines and actuators for 47 years. This fluid is hygroscopic, meaning it absorbs water from the atmosphere. Even in the dry Arctic air, some moisture absorption has occurred. Water in hydraulic systems causes 2 problems: corrosion of internal components and freezing. At -30 degrees, any water in the hydraulic system has frozen solid, potentially cracking seals and damaging the precision-machined cylinders in the hydraulic actuators. Larkins makes a decision. They won't attempt to retract the landing gear. The risk of hydraulic system failure is too high, and a gear-up landing on ice would destroy the aircraft. They'll fly it out with the gear down, accepting the aerodynamic penalty in exchange for certainty that the gear will support the aircraft during landing. By day 10, the team has completed initial assessment of all 4 engines and the primary aircraft systems. They compile their findings in a technical briefing conducted inside the heated crew tent, a canvas structure they've erected 50 yards from the bomber. Greenamyer reviews the status. Engine number 1, outboard port. Crankshaft rotates after heating and oil flush. Compression check shows all cylinders within acceptable limits. Magnetos require complete overhaul. Carburetor requires rebuild. Engine number 2, inboard port. Crankshaft rotates. Compression acceptable. 1 cylinder shows slightly low compression. Possible ring seating issue. Magnetos require overhaul. Carburetor requires rebuild. Engine number 3, inboard starboard. Crankshaft rotates freely after extensive flushing. Compression excellent on all cylinders. Magnetos require overhaul. Carburetor requires rebuild. This engine shows the most promise for first start attempt. Engine number 4, outboard starboard. Crankshaft rotates with difficulty. Compression check reveals 1 cylinder with 0 compression, likely stuck rings or valve damage. This engine may require cylinder replacement. Fuel system requires complete flush and cleaning. All fuel pumps must be rebuilt. Fuel tanks appear intact, but must be inspected internally before refilling. Hydraulic system. Landing gear hydraulics non-functional. Brakes hydraulics must be tested. Flight control hydraulics must be tested and certified before flight. Electrical system. Not yet assessed. Will require complete functional test of generators, voltage regulators, and distribution system. Pneumatic system. The B-29 used engine-driven compressors to pressurize the cabin and operate various systems. These compressors must be tested. The list is daunting, but Greenamyer sees a path forward. They'll focus resources on getting 2 engines running first. Number 2 and number 3, the inboard engines. These engines will provide electrical power via their generators, allowing them to test all electrical systems. Once those systems are verified, they'll tackle the outboard engines. The plan requires perfect execution. No wasted motion, no mistakes. They have 50 days remaining. On day 11, they achieve their first major milestone. Engine number 3 starts. The procedure is complex and requires precise coordination. First, they manually prime the engine by pouring premixed fuel oil directly into each cylinder through the spark plug holes. 16 ounces per cylinder, 18 cylinders total. This provides initial lubrication and combustion fuel without requiring the fuel pumps to work. Then they connect a portable ground power unit, a diesel generator providing 24-volt DC power to the aircraft's electrical system. This powers the engine starter motor. The starter motor on the R-3350 is a massive direct-drive electric motor that engages the engine crankshaft through a reduction gear. It draws 700 amps at 24 volts, 800 watts of electrical power when cranking. Krieger positions himself at the engine controls on the flight engineer's panel inside the aircraft. Greenamyer stands outside, watching the engine. Diemert operates the ground power unit. Krieger calls out, "Magnetos on, mixture rich, throttle cracked 1 inch, propeller full increase, ready to engage starter." Greenamyer responds, "Clear to start number 3. Krieger presses the starter button. The propeller rotates slowly. 1 blade, 2 blades, 3 blades. The engine turns through 2 complete revolutions, then 3. On the 4th revolution, cylinder number 5 fires, a sharp bang that echoes across the ice. Then cylinder 7 fires, then cylinder 1. The engine catches, coughs, belches a cloud of white smoke from the exhaust stacks, and settles into a rough idle. The sound is magnificent. The deep rumbling bark of 18 cylinders firing in sequence, the metallic whine of the reduction gear, the whoosh of the propeller blades cutting through Arctic air. The engine runs for 30 seconds. Then Krieger shuts it down, not because of any problem, but because they've accomplished the objective. They've proven that a Wright R-3350 engine that sat dormant for 47 years can run. The team stands in silence for a moment, watching smoke dissipate from the exhaust stacks. Then Diemert breaks into a grin that threatens to split his face. "We're going to fly this thing out," he says. "We're actually going to do this." But celebration is premature. Starting an engine for 30 seconds is vastly different from running it at full power for the hours necessary to fly from Greenland to Iceland, the planned first leg of the escape route. They need to run each engine through a complete test protocol: idle power, cruise power, takeoff power. They need to verify oil pressure, oil temperature, cylinder head temperature, fuel flow, and magneto performance at each power setting. They need to identify and fix any discrepancies before committing to flight. And they need to do this for all 4 engines. The real work is just beginning. Day 15 brings the first serious setback. They're conducting a full-power ground run on engine number 3, the engine that started successfully 5 days earlier. The procedure requires running the engine at takeoff power, 200 horsepower, 800 RPM, 48 inches of manifold pressure, for a sustained period to verify performance under maximum load. Krieger advances the throttle slowly, monitoring the instruments on the flight engineer's panel. The tachometer needle climbs: 1, 500 RPM, 1, 800 RPM, 2, 000 RPM. Oil pressure is steady at 75 psi. Cylinder head temperatures are rising, but within limits, between 225 and 245 degrees Celsius, across all 18 cylinders. At 400 RPM, they hear it, a metallic rattling sound from deep inside the engine, barely audible over the roar of the propeller, but distinctive enough to trigger immediate alarm. Krieger pulls the throttle back to idle, then shuts down the engine. The silence that follows is oppressive. They remove the engine cowling and begin inspection. The rattle could indicate any number of catastrophic failures: a broken connecting rod, a cracked piston, a failed bearing. Any of these would require complete engine disassembly, work that would consume weeks they don't have. After 2 hours of detailed inspection using a bore scope, a fiber optic camera that allows visual inspection inside the cylinders without disassembly, they locate the problem. It's not catastrophic, but it's serious. The exhaust valve in cylinder number 12 is sticking. The valve stem is corroded where it passes through the valve guide, causing it to hang open momentarily after the exhaust stroke. When it finally snaps shut, it creates the rattling sound. If left uncorrected, this condition will eventually cause the valve to break, sending metal fragments into the cylinder, which would destroy the piston, cylinder head, and potentially the entire engine. The solution requires removing the cylinder head, a complex procedure involving disconnecting fuel lines, ignition harnesses, exhaust manifolds, and 24 retaining nuts that must be torqued to precise specifications during reassembly. But there's a problem. They don't have a replacement exhaust valve. They have spare magnetos, spare fuel pumps, spare gaskets, but no spare exhaust valves. Dan Schley, the team fabricator, examines the damaged valve. It's a complex part, a 4.5-inch diameter tulip-shaped head made from Inconel superalloy, welded to a 9-inch stem of nitrided steel. The stem diameter is 0.4 to 375 inches, machined to tolerances of plus or minus 0.5 inches. Schley's assessment: I can machine a new stem from tool steel stock and weld it to the existing valve head. It won't be perfect, but it'll work. This is improvisation at the highest level. Schley sets up a makeshift machine shop inside one of the heated tents, using a portable lathe powered by a generator. He measures the original valve stem with micrometers, records every dimension, then turns a new stem from a piece of 4340 chrome moly steel rod. The work takes 16 hours. When he's finished, the new stem is dimensionally identical to the original. He welds it to the valve head using a TIG welder, heat treats the assembly to restore the metal's properties, then grinds and polishes the stem to the required surface finish. They install the repaired valve, reassemble the cylinder head, and torque all fasteners to specification. 65 foot-pounds for the head bolts, 35 foot-pounds for the rocker arm assembly, 180 inch-pounds for the intake manifold. On day 17, they run engine number 3 again. This time it runs smoothly through the entire power range. No rattles, no unusual vibrations. All temperatures and pressures within limits. They conduct a 10-minute full power run. The engine performs flawlessly. While engine work continues, Greenamyer Jr. tackles the electrical system, a challenge nearly as complex as the engines themselves. The B-29 electrical system was state-of-the-art for 1945, which means it's antiquated by 1994 standards, but still functional if properly maintained. The system operates on 24-volt DC power, supplied by 4 200-amp generators, one mounted on each engine's accessory gearbox. Each generator charges a 34-amp-hour nickel-cadmium battery located in the aft fuselage. The batteries provide power for engine starting and serve as backup power if generators fail. From the batteries and generators, power is distributed through a complex network of buses, circuit breakers, relays, and voltage regulators to hundreds of individual systems. Radios, navigation instruments, lighting, heating, gun turret motors, bomb bay door actuators, and countless others. The first challenge is the batteries. Nickel-cadmium batteries don't hold charge for 47 years. These batteries are certainly dead and possibly dangerous, as old NiCad batteries can develop internal shorts that cause thermal runaway and fire. They remove all 4 batteries and replace them with new aviation-grade lead-acid batteries brought from California. Lead-acid batteries are heavier but more reliable and easier to source. Next, they test the generators. With engine number 3 running, Greenamyer Jr. monitors the voltage output at the generator terminals. The reading should be 28.5 volts, slightly above the nominal 24-volt system voltage to ensure proper battery charging. The generator reads 22 volts, too low. The problem is the voltage regulator, a mechanical device that controls generator output by varying the field current. The regulator uses a carbon pile, a stack of carbon discs held together by spring pressure, to regulate voltage. Over time, the carbon oxidizes and the spring tension changes, causing drift in the output voltage. They don't have a spare voltage regulator. But Greenamyer Jr. discovers he can adjust the existing regulator by carefully bending the spring adjustment tabs and cleaning the carbon pile contacts. After 2 hours of trial and error adjustment, he achieves 28. 4 volts output. Close enough. They repeat this process for the remaining 3 generators as each engine is brought online. By day 22, all 4 engines have been started and run through initial testing. The status is encouraging. Engine 1 runs well. Slight roughness at idle smooths out at higher power settings. All temperatures and pressures normal. Engine 2, excellent performance across all power settings. This becomes their reference engine for comparison. Engine 3 runs perfectly after valve repair. No issues. Engine 4, the problem child. Compression test revealed 1 cylinder with 0 compression. Cylinder number 14. They remove the cylinder and find the problem. The piston rings are completely stuck in their grooves, corroded into place. The cylinder walls show scoring from the frozen rings scraping against aluminum. For engine 4, they face a critical decision. Repair the cylinder or leave the engine with 17 functional cylinders instead of 18. Running an engine with 1 dead cylinder isn't ideal. It creates power imbalance and vibration, but it's not impossible. Many R-3350 engines in military service flew missions with failed cylinders. Schley examines the damaged piston and cylinder. The cylinder barrel is salvageable. The scoring is superficial. But the piston is beyond repair. The ring grooves are too corroded to clean effectively. They need a new piston, and they don't have one. Greenamyer makes the call. We fly with engine 4 running 17 cylinders. It'll produce about 2,000 horsepower instead of 200. But 3 good engines and 1 slightly weak engine is enough for takeoff if we're light on fuel. This decision has profound implications for the escape plan. The B-29's maximum takeoff weight was 140 pounds. At that weight, the aircraft required all 4 engines producing full power, plus a 5,000-foot runway. They don't have a 5,000-foot runway. They have whatever they can build on the ice. And they won't be at maximum weight. They'll carry minimal fuel, no weapons, no ammunition, and a crew of only 2. Greenamyer as pilot and Diemert as flight engineer. Estimated weight, 85,000 pounds. But with 1 engine producing reduced power, their margin for error shrinks dramatically. The runway becomes the next critical challenge. The Kee Bird sits on the Greenland ice cap at approximately 400 feet elevation. The surface is not flat ice. It's compressed snow with an icy crust, interrupted by sastrugi, wind-formed ridges, and occasional crevasses. For takeoff, they need a runway at least 4,000 feet long, graded as flat as possible, oriented into the prevailing wind. They need to identify and mark any crevasses that could collapse under the aircraft's weight, and they need to compact the surface to provide sufficient support for the main landing gear. Each main gear carries approximately 28,000 pounds during takeoff roll. They have no grading equipment, no bulldozer, no steamroller. What they have is time, determination, and 1 piece of improvised equipment. A sled loaded with fuel drums filled with water, weighing approximately 4,000 pounds, which can be dragged behind a snowmobile to compact the snow surface. Larkins and Schley spend 10 days building the runway. They probe the ice with avalanche probes every 20 feet to detect hidden crevasses. They mark the runway boundaries with stakes topped with orange flags. They make hundreds of passes with the weighted sled, gradually compacting a 100-foot wide path stretching 200 feet across the ice. The work is brutal. Temperatures fluctuate between -10 and +20 degrees Fahrenheit. The wind never stops, constant 30-knot gusts that make every task exponentially harder. Larkins develops severe frostbite on 3 fingers of his left hand while probing for crevasses. Schley suffers first-degree burns on his face from windburn and sun reflection off the ice. But by day 33, they have a runway. While runway construction progresses, Krieg conducts progressively longer engine runs, gradually working up to full-power endurance testing. Each engine must run at takeoff power for at least 30 minutes to verify it can sustain maximum output without overheating, losing oil pressure, or developing mechanical problems. Engine 2 passes the test easily. Engine 3 passes with minor oil temperature concerns. The oil cooler, which should reduce oil temperature, shows reduced effectiveness. They flush the oil cooler with solvent and improve the performance slightly. Engine 1 develops a new problem during the endurance run: rough running at high power. The engine shakes noticeably, and the cylinder head temperature on cylinder number 5 climbs above maximum allowable limits, 265 degrees Celsius. They shut down and investigate. The problem is spark plug fouling. The spark plugs, massive 5-inch diameter units with platinum electrodes, have carbon deposits from the rich mixture used during initial starting. These deposits cause misfiring at high power settings. They remove all 36 spark plugs from engine 1, 2 plugs per cylinder. Clean them with solvent and a wire brush. Gap them to specification 20 inches and reinstall them. The next test run shows immediate improvement. Engine 4, running on 17 cylinders, produces 250 horsepower at full power, slightly better than the 200 horsepower estimate. The power loss is acceptable. By day 37, all 4 engines have been certified for flight operation. Greenamyer conducts a simultaneous 4-engine full-power run to verify that the electrical system can handle the load of all 4 generators operating at maximum output. The bomber sits on the ice, all 4 engines roaring at 800 RPM, propellers creating hurricane-force winds that blast snow and ice particles across the tundra. The sound is apocalyptic. 4 18-cylinder engines producing a combined 250 horsepower, the equivalent of 82 Formula One race cars at full throttle. Inside the cockpit, Greenamyer monitors the instruments. All readings are nominal. Generators producing 5 volts. Oil pressure steady. Cylinder head temperatures within limits. Fuel flow balanced. He lets the engines run for 15 minutes at full power, long enough to identify any problems that might surface during the takeoff roll. Nothing fails. Everything works. He pulls the throttles back to idle, then shuts down the engines in sequence. In the sudden silence, he can hear his own heartbeat. The B-29 is ready to fly. Day 40 marks a critical transition point. The engines work. The electrical system functions. The runway exists. But Greenamyer knows that starting engines and conducting ground runs is fundamentally different from entrusting your life to a 47-year-old aircraft at 10,000 feet over the Arctic Ocean. The flight control system requires comprehensive testing, a challenge complicated by the fact that you cannot fully test flight controls on the ground. But you can verify mechanical integrity, hydraulic function, and control surface movement. The B-29's flight control system is massive. The control yokes in the pilot and co-pilot positions connect through cables, pulleys, and bell cranks to 3 primary control surfaces: elevators, controlling pitch; ailerons, controlling roll; and rudder, controlling yaw. Each surface is enormous. The elevator span is 42 feet, the aileron span is 16 feet per side, the rudder stands 18 feet tall. These surfaces are too large for manual control at high speed. The pilot would need superhuman strength to deflect them against aerodynamic forces, so Boeing installed hydraulic boost systems, essentially power steering for aircraft, that amplify the pilot's control inputs by a factor of 20. Greenamyer sits in the left seat, the pilot's position, and begins the control check. He pushes the yoke forward. Through the windscreen, he watches the elevator on the horizontal stabilizer deflect downward. He pulls the yoke back. The elevator deflects upward. Full deflection in both directions. Functional. He rotates the yoke left. The left aileron rises, the right aileron drops. He rotates right. The controls reverse. Full deflection both directions. Functional. He presses the left rudder pedal. The massive rudder swings left. Right pedal. Rudder swings right. Full deflection. Functional. But mechanical movement doesn't guarantee the hydraulic boost system works properly. That requires engine operation to pressurize the hydraulic system and actual control force testing. With engines running, Greenamyer monitors hydraulic pressure at the flight engineer station. 200 psi, within normal limits. Greenamyer cycles the controls again, this time feeling for any unusual resistance or binding. The controls feel heavy, much heavier than they should. The hydraulic boost is providing assistance, but not as much as specified in the technical manual. This could indicate internal leakage in the hydraulic actuators, worn seals, or air in the hydraulic lines. They don't have time for a complete hydraulic system overhaul. Instead, they bleed the system thoroughly to remove air, top off the hydraulic reservoirs with fresh MIL H5606 fluid, and test again. The control forces improve slightly, but remain heavier than ideal. Greenamyer makes a note. The takeoff rotation will require more force than normal. He'll need to anticipate this and begin rotation earlier in the takeoff roll. The next critical system is the brakes. The B-29 uses hydraulic disc brakes on the main landing gear, massive multi-disc assemblies capable of stopping 140 pounds from landing speed. But these brakes haven't been used in 47 years. Demert pressurizes the brake system and checks for leaks. Hydraulic fluid weeps from several brake line fittings. The copper crush washers have hardened with age and no longer seal properly. They replace every suspect washer, retorque the fittings, and test again. No leaks. With engines running at idle power, Greenamyer tests the brakes. He presses the toe pedals, the brake controls located on the rudder pedals. The aircraft lurches slightly as the brakes engage. He releases pressure. The brakes release. But there's a problem. The left brake grabs harder than the right. This asymmetry will cause the aircraft to pull left during braking, potentially dangerous during landing when directional control is critical. They jack up the left main gear, an exhausting process involving manually pumping a 20-ton hydraulic jack, and remove the left wheel. The brake disc shows uneven wear, and 2 of the 6 brake pads are contaminated with hydraulic fluid from a slow leak. They clean the pads with solvent, resurface them with emery cloth, replace the leaking seal, and reassemble the brake. The next test shows improved balance between left and right brakes. Day 43 brings weather challenges. A storm system moves across the ice cap, bringing temperatures down to -15 degrees and winds gusting to 50 knots. Work stops completely. The team retreats to their heated tents and waits. During the enforced downtime, Greenamyer reviews the escape route in detail with Demert. The plan is ambitious. Leg 1. Greenland ice cap to Kulusuk, Greenland, a small airport on the eastern coast with a 200-foot gravel runway. Distance, 220 nautical miles. Flight time, approximately 90 minutes. Leg 2. Kulusuk to Reykjavik, Iceland. Distance, 460 nautical miles. Flight time, approximately 3 hours. Leg 3. Reykjavik to Scotland, either Prestwick or Glasgow. Distance, 780 nautical miles. Flight time, approximately 5 hours. Final legs, Scotland to England, then across Europe to Greenamyer's facility in California via multiple stops for fuel and maintenance inspection. Total distance from the ice cap to California, approximately 500 nautical miles. The critical leg is Leg 1, the flight from the ice cap to Kulusuk. This segment presents maximum risk because they'll be flying over uninhabited ice and ocean with no emergency landing options. Weather in East Greenland is notoriously unstable. Conditions can deteriorate from clear to instrument meteorological conditions in minutes. The aircraft will be heavy with fuel, approximately 3,000 gallons for the 220 nautical mile flight, providing minimal reserve. They'll be flying an aircraft that hasn't flown in 47 years, with systems that have been minimally tested. If anything goes wrong during Leg 1, engine failure, control system failure, fuel system problem, their options are extremely limited. Ditching in the Arctic Ocean means death within minutes from hypothermia. Landing back on the ice cap requires turning around immediately, and the improvised runway only works in one direction. They haven't built a runway at the opposite end. Greenamyer understands these risks completely. He's a test pilot by temperament and training. He's flown dozens of first flights in experimental and restored aircraft. But this is different. This is flying a strategic bomber that sat dormant for half a century, restored with improvised parts in Arctic conditions, with no backup and no safety net. The weather clears on day 45. They have 15 days remaining before temperatures drop below survivable working conditions. Greenamyer makes the decision. They'll conduct taxi tests on day 46, then attempt the flight to Kulusuk on day 48 if all systems check out. The taxi test is essential. It's the only way to verify that the aircraft can actually move under its own power. that the brakes work under dynamic loads, that the engines produce sufficient thrust, and that the improvised runway can support the aircraft's weight without collapsing. On the morning of day 46, they prepare the aircraft for the taxi test. They load 800 gallons of fuel, enough for extended engine runs, but not enough to make the aircraft dangerously heavy. They conduct final pre-taxi inspections, tire pressures, fluid levels, control surface security, engine cowling fasteners. Greenamyer and Diemert board the aircraft. Greenamyer takes the left seat. Diemert occupies the flight engineer's station directly behind the cockpit. They're the only two people aboard. Everyone else retreats to a safe distance in case something goes catastrophically wrong. Greenamyer follows the startup checklist from memory. He started these engines dozens of times over the past 6 weeks. Batteries on, fuel boost pumps on, mixture controls rich, throttles cracked 1 inch, propellers full increase. Engine number 3 starts first. It's always been the most reliable. The familiar rumble fills the cockpit. Engine number 2 starts 10 seconds later. Engine 1 requires 20 seconds of cranking before it catches. Engine 4, the 17-cylinder engine, coughs twice before settling into its slightly rough idle. He lets the engines warm for 5 minutes, monitoring oil pressure and temperature. All readings normal. Throttles forward slightly. The engines respond. The propeller noise increases. The aircraft begins to move. For the first time since February 21, 1947, 17,142 days ago, the Kee Bird is moving under its own power. Greenamyer advances the throttles further. The aircraft accelerates. Snow and ice particles blast backward from the propellers. The main gear tires leave tracks in the compacted snow runway. 10 knots, 20 knots, 30 knots. He tests the brakes, toe pedals pressed firmly. The aircraft decelerates. The brakes hold, no pull to either side. He releases the brakes and accelerates again. 40 knots, 50 knots. At 50 knots, he can feel the controls becoming aerodynamically effective. The ailerons produce roll forces. The rudder provides yaw control. The elevator responds to yoke input. 60 knots, 70 knots. He's not trying to take off, not today, but he wants to feel what happens at rotation speed. The technical manual specifies rotation at 105 knots for an 85,000 pound aircraft. At 70 knots, he pulls the throttles back to idle and applies brakes. The bomber slows smoothly and stops after 200 feet. They taxi back to the starting point and conduct 3 more high-speed runs, progressively faster each time. On the final run, they reach 90 knots, close enough to rotation speed to verify that the aircraft is controllable and that the runway surface will support the takeoff loads. Everything works. The aircraft is ready. That evening, Greenamyer briefs the team on the final flight plan. Takeoff weight, 87,000 pounds. Aircraft empty weight, 74,000 pounds, plus fuel and crew. Fuel load, 200 gallons, approximately 200 pounds at 6 pounds per gallon. Calculated takeoff distance, 800 feet to rotation speed, plus 400 feet ground roll after rotation before liftoff. Total, 200 feet, which exactly matches their runway length. Margin for error, 0. If the engines don't produce full power, they won't lift off before running out of runway. If the runway surface is softer than expected, increasing rolling resistance, they won't reach rotation speed. If wind conditions are unfavorable, they'll need additional runway length they don't have. Greenamyer reviews the abort criteria. If we're not at 100 knots by the 500-foot marker, I'm aborting. If any engine fails before rotation, I'm aborting. If we experience any control system anomaly, I'm aborting. Once we rotate, once the nose gear leaves the ground, we're committed. There's no stopping at that point. The team spends day 47 conducting final preparations. They drain and refill the fuel tanks with fresh 100-octane aviation gasoline. 200 gallons pumped from drums that were flown in specifically for the escape flight. They conduct final engine runs on all 4 engines. They verify that all required equipment is aboard. Fire extinguishers, emergency oxygen, survival gear, ELT, emergency locator transmitter, radios. They file a flight plan with Kulusuk Airport, notifying them to expect the arrival of a B-29 bomber, an unusual occurrence that generates considerable interest from the Greenlandic aviation authorities. That night, Greenamyer sleeps poorly. Not from fear, he's too experienced for pre-flight anxiety, but from the mental rehearsal process. He visualizes every phase of the flight: the takeoff roll, the rotation, the initial climb, the level off at cruise altitude, the navigation to Kulusuk, the approach, the landing. He visualizes failures: engine fire during takeoff, hydraulic failure in flight, landing gear malfunction. For each failure mode, he mentally rehearses the emergency procedures. This is what test pilots do. They don't hope nothing goes wrong. They assume something will go wrong and prepare to handle it. Day 48 arrives clear and cold. Temperature -5 degrees Fahrenheit. Wind 10 knots from the north, nearly straight down the runway. Visibility unlimited. Perfect conditions. At 800 hours local time, Greenamyer and Diemert board the Kee Bird for the last time it will ever sit on Greenland ice. The startup sequence proceeds without incident. All 4 engines start on the first attempt. Oil pressures stabilize at 75 psi. Cylinder head temperatures climb into the normal operating range. Electrical system shows 4 generators online, producing 28.5 volts. Greenamyer completes the pre-takeoff checklist. Diemert verifies each item. Fuel boost pumps, on. Mixture controls, auto-rich. Propeller governors, 2, 800 RPM. Flaps, 20 degrees. Elevator trim, 3 degrees nose up. Rudder trim, neutral. They've decided on 20-degree flap deflection for takeoff, a compromise between maximum lift, which requires 40 degrees, and minimum drag, which requires 0 degrees. The 20-degree setting provides adequate lift for the relatively light 87.00 pound takeoff weight while keeping drag manageable. Greenamyer advances the throttles to takeoff power. All 4 engines respond simultaneously, climbing to 2, 800 RPM and 48 inches of manifold pressure. The noise is overwhelming even through their headsets. 250 horsepower producing approximately 32.00 pounds of thrust. He releases the brakes. The Kee Bird begins its takeoff roll. 20 knots. The rudder becomes effective. He can steer with pedal inputs rather than differential braking. 40 knots. The ailerons become responsive. He makes small corrections to keep the aircraft centered on the runway. 60 knots. The elevator gains authority. He can feel pressure building on the yoke as aerodynamic forces increase. 80 knots. The main gear tires pound across irregularities in the compacted snow surface. The airframe shakes and vibrates. Every rivet, every structural joint, every panel experiences loads it hasn't felt in 47 years. 90 knots. They pass the 3.00 foot marker. 200 feet of runway remaining. 100 knots. They pass the 500 foot marker. Greenamyer's abort decision point. All 4 engines are producing full power. All systems normal. They're committed. 105 knots. Greenamyer pulls back on the yoke. The nose gear lifts off the ice. The bomber rotates to an 8-degree nose-up attitude. For 3 seconds, the main gear remains on the surface as the wings generate lift. The weight transfers from the landing gear to the wings. The struts extend slightly as compression loads decrease. Then, at 108 knots and 150 feet down the runway, the main gear separates from the ice. The Kee Bird is flying. Greenamyer maintains 8 degrees nose up and allows the airspeed to build to 120 knots, the best rate of climb speed for their weight. The vertical speed indicator shows 400 feet per minute climb rate. They're climbing. They're flying. The impossible has happened. Diemert monitors the engine instruments. All engines normal. Oil pressure 75, oil temp 90 degrees, CHT 240. Fuel flow balanced at 350 gallons per hour total. At 500 feet above the ice, Greenamyer begins a gentle climbing left turn to intercept the course to Kulusuk, heading 095 degrees magnetic. The bomber responds smoothly. The heavy control forces he experienced on the ground are less noticeable in flight. The aerodynamic forces provide feedback that makes the controls feel more natural. At 1,000 feet, he levels off temporarily to retract the flaps. The flap handle requires significant force. The hydraulic system is still not providing full boost, but the flaps retract normally. The aircraft accelerates to 140 knots. He resumes the climb. targeting 8,000 feet for cruise, high enough to clear any terrain along the route, low enough to avoid needing supplemental oxygen. At 3,000 feet, engine number 4 develops a slight vibration. Greenamyer notices it first. Number 4 running rough, oil pressure dropping, now reading 65 psi. 65 psi is below normal but not immediately dangerous. The minimum allowable oil pressure is 55 psi. But decreasing oil pressure indicates a developing problem, possibly a failing oil pump or an internal leak. Greenamyer makes a decision. Pull number 4 back to cruise power. Let's see if the vibration and oil pressure stabilize at reduced power setting. Greenamyer retards the number 4 throttle to 200 RPM and 35 inches manifold pressure, cruise power instead of climb power. The vibration decreases noticeably. The oil pressure stabilizes at 68 psi. They continue climbing on 3 3/4 engines. The climb rate decreases to 300 feet per minute, but they're still climbing. At 8,000 feet, Greenamyer levels off and establishes cruise configuration. All 3 healthy engines at 200 RPM and 35 inches manifold pressure, engine 4 at 2,000 RPM and 32 inches, just enough to contribute without making its condition worse. The indicated airspeed settles at 180 knots. Ground speed, calculated by timing their progress over recognizable ice features, is approximately 195 knots. They have a tailwind. The flight progresses smoothly for 40 minutes. They cross the edge of the ice cap and fly over the coastal mountains of East Greenland, jagged peaks rising to 10,000 feet, glaciers filling the valleys between them. The scenery is spectacular and utterly hostile. If they had to land anywhere below them, survival would be measured in minutes. At 1 hour into the flight, they establish radio contact with Kulusuk Airport. Kulusuk Tower. This is Kee Bird, B-29 aircraft, 60 miles west, inbound for landing. There's a long pause. Then, Kee Bird, Kulusuk Tower. Say again, aircraft type? B-29 Superfortress, World War II bomber. Be advised we have 1 engine running reduced power and will need priority handling for landing. Another pause. Kee Bird, roger. You are cleared for straight-in approach runway 07. Winds 090 at 12 knots. Airport firefighting equipment will be standing by. At 20 miles from Kulusuk, they begin descent. Greenamyer reduces power on all engines and extends the landing gear. The hydraulic system groans, the pumps struggling to move fluid through cold, stiff actuators, but the gear extends and locks down. 3 green lights illuminate on the instrument panel. Left main, right main, nose gear down and locked. At 10 miles, he extends 20 degrees of flaps. The bomber slows to 140 knots, approach speed for their landing weight. At 5 miles, he can see Kulusuk Airport, a single gravel runway carved into a fjord, surrounded by mountains on 3 sides and the ocean on the 4th. It's a challenging approach under the best conditions. At 2 miles, Greenamyer calls out, "Smoke in the cabin! I've got smoke coming from behind my station." Greenamyer smells it immediately. Acrid electrical smoke, the distinctive odor of burning insulation. "Location?" he demands. "Behind the flight engineer's panel. I can't see flames, but there's definitely smoke. It's getting thicker." They're less than 2 minutes from landing. Greenamyer has 3 options. Abort the approach, climb to a safe altitude, and troubleshoot the electrical fire. Continue the approach and land immediately at Kulusuk. Shut down all electrical power to stop the fire, which means losing all radios, instruments, and flight controls that depend on electrical power. He makes the decision instantly. "We're landing. Now, pull the master battery switch if the smoke gets worse. But give me as much electrical power as you can until we're on the ground." Greenamyer acknowledges. The smoke continues to thicken, but doesn't worsen dramatically. 1 mile from the runway threshold, Greenamyer focuses entirely on the landing. Airspeed 130 knots. Sink rate 400 feet per minute. Runway aligned. At 1/2 mile, he extends full flaps, 40 degrees. The bomber slows to 120 knots. The sink rate increases to 600 feet per minute. He adds power on the 3 good engines to arrest the descent. They cross the runway threshold at 110 knots, 10 knots above target approach speed, but acceptable given the emergency. The main gear touches down hard on the gravel surface. Greenamyer deploys the thrust reversers, clamshell doors that redirect engine exhaust forward to provide braking force, and applies maximum braking. The bomber decelerates rapidly. Rocks and gravel blast up from the tires, pinging against the aluminum fuselage. At 60 knots, he releases the brakes momentarily to let the tires cool, then reapplies them. The aircraft stops with 200 feet of runway remaining. They've made it. The Kee Bird has escaped the ice, but the smoke in the cabin is now dense enough to obscure visibility. Diemert pulls the master battery switch, killing all electrical power. The smoke stops getting worse, but doesn't dissipate. "Emergency egress!" Greenamyer orders. "Get out now!" They evacuate through the forward hatch, dropping 8 feet to the gravel runway. Airport firefighting trucks race toward them, sirens wailing. As Greenamyer stands on the runway, watching firefighters spray foam into the cabin, he experiences a complex mixture of emotions. Relief that they survived, satisfaction that they proved it could be done, and profound disappointment that the mission ended this way, with an electrical fire instead of a triumphant arrival. The fire crews extinguish the smoldering electrical fire within minutes. The damage is limited to a section of wiring harness behind the flight engineer's panel, apparently a short circuit in a voltage regulator caused by vibration during flight, which heated the wiring until the insulation ignited. But the fire revealed something more ominous. When they inspect the aircraft thoroughly after the fire is extinguished, they discover evidence of a fuel leak in the aft fuselage. A slow seep from a fuel transfer line that has created a sheen of gasoline on the fuselage interior surfaces. If the electrical fire had propagated just a few feet further aft, it would have ignited the fuel vapors. The resulting fire would have been catastrophic and unsurvivable. They were seconds away from dying. Greenamyer makes the decision immediately. "We're not flying this aircraft again until we've done a complete electrical system overhaul and fixed the fuel leak. That's going to take weeks, maybe months." The Kee Bird remains at Kulusuk for 6 weeks while Greenamyer arranges for parts, tools, and additional technicians to be flown in. They repair the electrical fire damage, replace hundreds of feet of degraded wiring, and seal the fuel leak. During this time, Greenamyer formulates a new plan. The original escape route, flying the bomber across the Atlantic via Iceland and Scotland, is too risky given the aircraft's condition. Instead, they'll attempt a shorter flight. Kulusuk to Reykjavik, Iceland, then disassemble the aircraft and ship it by cargo vessel to California. It's not the heroic flight he envisioned, but it's pragmatic. They spend day 120 preparing for the second attempt, the flight from Kulusuk to Reykjavik. This time, they conduct even more thorough pre-flight inspections. They run all 4 engines for hours, monitoring for any anomalies. They test every electrical circuit. They pressure test the fuel system. Everything checks out. On day 122, they attempt the flight to Reykjavik. The takeoff from Kulusuk is normal. All 4 engines perform well. Even engine 4 runs smoothly at full power. They climb to 10,000 feet and establish cruise flight at 190 knots. The flight progresses without incident for 90 minutes. They're halfway to Reykjavik when Diemert notices something wrong. Oil temperature climbing on number 2, now reading 110 degrees. That's above limits. Normal oil temperature is 90 degrees Celsius maximum. 110 degrees indicates the oil is breaking down, losing its lubricating properties. If it continues rising, the engine will seize. Greenamyer reduces power on engine number 2. The oil temperature stabilizes at 108 degrees but doesn't decrease. 20 minutes later, engine number 2 begins vibrating. The oil pressure drops from 75 psi to 60 psi, then to 55 psi, the minimum allowable. Shutdown number 2, Greenamyer orders. Feather the propeller. Diemert pulls the mixture control to idle cutoff. Engine number 2 spools down. He activates the propeller feathering control, which rotates the propeller blades edge onto the airflow, minimizing drag. They're now flying on 3 engines. But 3 engines are enough. The B-29 was designed to fly on 2 engines if necessary. With 3 engines, they can maintain altitude and airspeed without difficulty. They continue to Reykjavik and land without further incident. The post-flight inspection reveals that engine number 2 suffered a bearing failure, specifically the number 3 main bearing, which supports the crankshaft. The bearing overheated due to inadequate lubrication, probably because internal oil passages were partially blocked by residual sludge that wasn't completely flushed during the Arctic restoration. The bearing failure is repairable, but it requires complete engine disassembly, a process that will take weeks in a proper maintenance facility. Greenamyer faces reality. The Kee Bird cannot fly across the Atlantic in its current condition. The engines are simply too degraded, despite their best efforts at restoration. The aircraft needs a complete overhaul. New engines or rebuilt engines, overhauled fuel system, new electrical system, structural inspection and repair. Such work will cost hundreds of thousands of dollars and take months. He makes the painful decision. They'll dismantle the aircraft at Reykjavik and ship it by sea to California. It's an admission that the full escape flight isn't possible, but at least the bomber will be saved for eventual restoration. But before they can begin disassembly, they need to move the aircraft from Reykjavik Airport to a storage facility. The airport authority wants the aircraft off the active ramp. They decide to taxi it to a remote parking area rather than towing it. Towing requires equipment they don't have readily available. This decision will prove catastrophic. Day 130. Reykjavik, Iceland. Temperature, 45 degrees Fahrenheit. Wind, calm. Weather, overcast but dry. The plan is simple. Start engines 1 and 4, the outboard engines, and taxi the bomber 1/4 mile to the storage area. It's a routine operation that should take 10 minutes. Greenamyer and Diemert board the aircraft. They complete the engine start checklist. Engine number 1 starts normally. Engine number 4 requires extended cranking but eventually catches and runs smoothly. They release the parking brake and begin taxiing. The bomber rolls slowly across the concrete ramp, following the yellow taxiway line toward the storage area. Everything is normal for the first 5 minutes. Then Diemert smells it. Hot oil. The distinctive odor of overheated lubricant. Oil smell, he reports. Can't identify which engine. Greenamyer scans the engine instruments. Oil temperatures and pressures are normal on both running engines. But the smell is getting stronger. It's not the running engines, Diemert says. I think it's coming from number 3. Engine number 3, the inboard starboard engine, isn't running. It's been shut down since they landed. But it's still warm from the flight. And residual oil in the engine is pooling in the lower cylinders and crankcase, slowly seeping past seals that have degraded from decades of thermal cycling. This is normal. Engines leak after shutdown. The oil pools creates a smell, but doesn't present a hazard under normal circumstances. But these aren't normal circumstances. As they taxi, the propeller on engine number 3, which is windmilling slowly in the slipstream, generates heat through friction in the reduction gear and propeller hub. This heat, combined with the heat from the adjacent running engine number 4, creates a hot zone near the engine cowling. And somewhere in that hot zone, oil vapors reach their flash point. The fire starts small. A wisp of smoke from the number 3 engine cowling. Barely visible. Diemert sees it first. Smoke. Number 3 cowling. We've got a fire. Greenamyer immediately shuts down both running engines and pulls the fire suppression handles for engine number 3. This action does 2 things. It closes the fuel shutoff valve to prevent fuel from feeding the fire, and it discharges a CO2 bottle directly into the engine compartment to smother the flames. The CO2 discharge should extinguish the fire within seconds. It doesn't. The fire intensifies. Flames become visible through the cowling seams, bright orange tongues licking out from the engine compartment. "Emergency egress!" Greenamyer shouts. "Get out now!" They evacuate through the forward hatch. As Greenamyer's feet hit the concrete, he looks back at the bomber and realizes with horror that the fire is spreading faster than should be possible. Airport firefighting trucks are already responding. They were staged nearby as a precaution, but they're 200 yards away and accelerating toward the burning bomber. The fire reaches the wing fuel tanks. What happens next occurs in less than 20 seconds, but to everyone watching, it seems to unfold in slow motion. The fuel vapors in the number 3 main fuel tank, approximately 200 gallons of 100-octane aviation gasoline that wasn't completely drained, ignite. The explosion is not dramatic like a movie explosion. There's no fireball, no shockwave. Instead, the tank ruptures and fuel pours out, feeding the fire. Flames spread across the wing surface, following the rivulet of burning fuel. The aluminum wing skin, alloy 24est, with a melting point of 916 degrees Fahrenheit, begins to soften and warp under the intense heat. The fire reaches the number 4 engine, still hot from running minutes earlier. The residual oil in that engine ignites. Now 2 engines are burning. The firefighting trucks arrive and begin spraying foam, but the fire has too much fuel. The foam smothers flames in some areas only to have them reignite seconds later as fresh fuel seeps from ruptured tank baffles. The wing structure begins to fail. The main wing spar, the massive I-beam that carries the primary flight loads, weakens as the aluminum reaches critical temperature. The starboard wing begins to sag, drooping toward the concrete. More fuel pours from the sagging wing, feeding the inferno. The fire spreads aft along the fuselage, consuming the radio compartment, the crew bunks, the waist gunner stations. Everything inside the fuselage that can burn does burn. Insulation, wiring, fabric headliners, plywood panels, seats, oxygen hoses. The firefighting crews continue spraying foam, but they're fighting a losing battle. The fire has compromised the aircraft structure so severely that attempting to save it would risk the lives of the firefighters. After 30 minutes, the fire chief makes the decision to let it burn under controlled observation, rather than risk personnel trying to save what's clearly beyond salvation. By the time the fire finally exhausts its fuel supply 90 minutes later, the Kee Bird is destroyed. The starboard wing has collapsed completely, the main spar severed by thermal failure. The fuselage is burned through in multiple locations, the aluminum skin consumed by fire, the structural frames exposed and warped. The tail section, which survived the initial fire, is so heat damaged that the metal is stress-relieved and structurally worthless. Engine number 3, where the fire started, is a melted mass of aluminum and steel. Engine number 4 is similarly destroyed. Engines 1 and 2, on the port wing, survived relatively intact. But the wing structure between them is so damaged that removing the engines for salvage would require cutting through compromised metal. Greenamyer stands 200 yards away, watching the smoke rise from the wreckage. He doesn't speak. There's nothing to say. 47 years in the ice, 60 days of brutal Arctic restoration work, 2 successful flights covering hundreds of miles, countless hours of engineering problem-solving, improvised manufacturing, and determined effort. All destroyed in 90 minutes because of an oil leak and a hot engine cowling. The investigation into the fire is conducted by Icelandic aviation authorities in cooperation with the aircraft's insurance carrier. The findings are straightforward and damning. Cause: oil vapor ignition in engine number 3 due to accumulated oil in the cowling combined with heat from the adjacent running engine and friction-heated propeller hub. Contributing factors: degraded oil seals allowing excessive oil seepage, inadequate ventilation in the engine cowling, decision to taxi with only 2 engines running, which created asymmetric heating conditions. Preventability: the fire could have been prevented by either 1. Towing the aircraft instead of taxiing it, or 2. Starting all 4 engines for taxiing, which would have provided symmetric cooling airflow across all engine compartments. The report concludes with a single sentence that summarizes the entire tragic outcome. An abundance of caution regarding fire risk was not exercised given the known condition of the aircraft and its engines. Greenamyer receives a copy of the report 6 weeks after the fire. He reads it once, files it away, and never speaks publicly about it. But privately, he's devastated. Not by the financial loss. The aircraft was insured, though not for its full historical value, but by the knowledge that the Kee Bird came so close to survival. They proved it could be done. They started engines that hadn't run in 47 years. They flew an aircraft that every expert said was unflyable. They executed one of the most audacious aircraft rescue operations in aviation history, and then they destroyed it through a single lapse in judgment during what should have been a routine taxi operation. The wreckage of the Kee Bird remains at Reykjavik airport for 3 months, while Greenamyer negotiates with Icelandic authorities about disposal. The bomber is too damaged to restore. Shipping it to California would cost more than the salvageable parts are worth. Eventually, the wreckage is sold to a scrap metal dealer who cuts it into pieces and processes it for recycling. Some components are salvaged by collectors: instruments, control yokes, the nose art panel showing the Kee Bird cartoon character. But the vast majority of the aircraft, 58. 0 pounds of aluminum alloy, steel, and copper is melted down and recycled. The only substantial pieces that survive intact are the 4 Wright R-3350 engines, or what's left of them. 2 are destroyed by fire. 2 are damaged but potentially rebuildable. These engines are purchased by a warbird restoration shop in Texas, where they'll eventually be used as parts donors for other R-3350 engines in flying B-29s and Douglas Sky Raiders. So in a sense, pieces of the Kee Bird do fly again, just not as a complete aircraft. The story of the Kee Bird spreads through the warbird restoration community, the aviation press, and eventually the general public through a documentary film produced by Nova, the PBS science series. The documentary, titled B-29 Frozen in Time, airs in 1996 and reaches millions of viewers. The film presents the rescue mission as both an inspiring tale of human determination and a cautionary story about the limits of what can be accomplished with improvised resources. It doesn't dwell on the fire. The filmmakers focus more on the Arctic restoration work and the successful flights, but it doesn't shy away from the tragic ending either. Public reaction to the story is mixed. Some viewers see it as a heroic effort that almost succeeded. Others see it as a reckless endeavor that destroyed a priceless historical artifact. Both perspectives are valid. What's undeniable is that Greenamyer and his team accomplished something genuinely extraordinary. They resurrected a strategic bomber that had been written off as unrecoverable. They made it fly after 47 years of dormancy. They proved that with sufficient skill, determination, and improvisation, even the most improbable engineering challenges can be overcome. The fact that the mission ultimately failed doesn't diminish what they achieved. It just adds a note of tragedy to a story that could have been purely triumphant. Technical Appendix: Understanding the B-29 Superfortress. For those interested in the engineering details, the B-29 represented the pinnacle of 1940s aviation technology. Dimensions: length, 99 feet. Wingspan, 141 feet. Height, 27 feet 9 inches. Wing area, 736 square feet. Weights: empty weight, 500 pounds. Maximum takeoff weight, 140 pounds. Performance: maximum speed, 357 mph at 25 feet. Cruise speed, 220 mph service ceiling, 850 feet range, 250 miles with 10 pound bomb load. Power plants: 4 Wright R-3350, 23. Duplex cyclone radial engines, 18 cylinders per engine, 2 banks of 9. Displacement: 350 cubic inches per engine. Power output: 200 horsepower per engine at takeoff armament. Original WWE configuration. 10. 50 caliber Browning M2 machine guns in remote-controlled turrets. 2. 50 caliber guns and 120mm cannon in tail turret. Maximum bomb load: 20 pounds. Crew: 11. Pilot, co-pilot, bombardier, flight engineer, navigator, radio operator, radar operator, 4 gunners, tail gunner. Production: 3 1970 aircraft built between 1943 and 1946. Cost per aircraft: approximately $640. 0 in 1945, equivalent to $10. $5 million in 2024. The B-29 was the most expensive weapons development program of World War II, costing $3 billion total, more than the Manhattan Project. Its technological innovations included pressurized cabin, first production bomber with a fully pressurized crew compartment, allowing operation at altitudes above 30 feet without crew oxygen masks. Remote-controlled gun turrets, computer-assisted fire control system that allowed gunners to operate turrets remotely using periscopic sights. Advanced aerodynamics, high aspect ratio wing design, and Fowler flaps for maximum efficiency. Sophisticated engines. The R-3350 engines featured 2-stage supercharging, fuel injection, and advanced cooling systems. These innovations came at a cost. The B-29 was notoriously difficult to maintain, suffered from frequent engine fires, and required highly trained crews. But it was also the most capable bomber of its era, able to deliver devastating payload across unprecedented distances. The Kee Bird was one of 3 970 B-29s built. Of those, only 2 remain in flying condition today. Fifi, operated by the Commemorative Air Force, and Doc, operated by Doc's friends. Both aircraft require continuous, expensive maintenance to keep them airworthy. The loss of the Kee Bird meant that one fewer B-29 would ever join that elite group of flying survivors. What if they had succeeded? It's worth considering what would have happened if the Kee Bird had completed its escape flight successfully. If the electrical fire hadn't occurred, if the engine bearing hadn't failed, if the taxi fire hadn't destroyed the aircraft. If everything had gone right, the bomber would have reached California in late 1994. Greenamyer would have spent the following years conducting a complete restoration. New engines, new electrical systems, new hydraulics, structural reinforcement, cosmetic restoration. The work would have cost $2 to $3 million and taken 5 to 7 years. But by 2000, the Kee Bird would have been the third flying B-29 in existence, a genuine warbird worth perhaps $5 to $8 million to collectors. Greenamyer would have recouped his investment through airshow appearances, where a flying B-29 commands $15,025 per show, plus offering rides to paying passengers at $1, $500 to $2,000 per person. More importantly, the aircraft would have served an educational purpose, giving new generations the opportunity to see and experience a piece of World War II history that played a crucial role in ending the Pacific War. Instead, that opportunity was lost forever. The last time anyone saw the Kee Bird intact was in February 1947, when the crew walked away from it on the Greenland ice. Everyone who witnessed the rescue attempt in 1994 to 1995 saw only a partial success, a bomber that flew again briefly before being destroyed. No one will ever see the Kee Bird fly again. But the story endures, and perhaps that's the real legacy. Not the aircraft itself, but the proof that impossible challenges can be overcome, that preserved history can be resurrected, and that human determination can accomplish extraordinary things even when the odds seem insurmountable. The Kee Bird died twice. Once in 1947 when it made that emergency landing on the ice, and again in 1995 when it burned on a Reykjavik taxiway. But in between those two deaths, for a few brief hours, it lived again. And that makes all the difference.